This is a part 2 video for how to design an RL agent for a system with a Sparse reward. If you haven't watched the first part, I will put the link at the end of the video. Make sure to watch that one first and then come back in here. In the previous part, I talked about the challenges and the problems that you might encounter when you are designing an agent with a Sparse reward. We suggested Actor-Critic method with a replay buffer. I talk about what is the concept of a prioritized replay, and we also went over some of the tweaks that we can do on your reward shaping and also in your agent design to make sure that you avoid your policy collapse or for example exploration versus exploitation and the other challenges. So for this one I will go over the code. Welcome everyone to your channel AI Fun Fact Follow. For those of you who are new to this channel, my name is Pedro Magan, a PhD student in computer science, and in this channel we talk about AI and machine learning for our everyday life. For this type of video, I'm going to talk about the design and the code that we need for an Actor algorithm or Actor-Critic with experience replay. So we'll go over different components, and then I will also show you the result in Wandb and how we come up with the changes that we suggested in the previous part, and you can see that how the code is going to look like. I will put the link of this code inside the description of the video. On the top of the code, as always, we have our import. So we have the torch function, numpy, the optim, the random, the deck, which actually didn't use it. We have the gym environment, we had matplotlib and Wandb to show the results. So this is the init of the project. I'm going to show you two approaches for the replay buffer. The first one is the normal replay buffer without the prioritize, which we talked on the previous video, and we said very quickly, if I want to recap, we said that since it is a sparse reward, there are some transitions that have a higher priority, so they contain higher reward and they even contain a low reward. We want to have them get somewhat of priority, and we don't remember them like very quickly because those actually contain more information. But at the same time, we shouldn't just have them always there because we go on and it is an on policy approach and we learn new things, and the previous thing that we learn might not be as helpful. So in the first one in here, we have the normal replay buffer. So in it we define its capacity, the maximum length that it can get, the puff buffer, which is basically the list of the items that we have, and the position and the average reward. So basically you can actually ignore the average reward. It's not going to be used in here, and the position is actually defined the index that we are in. There is other approach to implement this as well by just the deck. Each time you're gonna push it, and then the element that was first in is gonna be out first, or the FIFO. But in here I also try to have another approach which I iterate the position each time. So basically I'm not like changing the deck size. So I define a method add, which basically if it is not full capacity, we add a none, and then at that specific position, which is the none position, we are going to add all of this in a tuple format, which is state action reward next state done, and then log probability. So this log probability will be used later on for our importance sampling. More on that later in the video. And then the position obviously is going to be added by 1, but then we need to compute the module to the capacity of it. And then here I computed the average. Again, I said that the average is not important in here, but obviously somebody might ask like how you can compute the average reward of it. basically a buffer. So this is how you do it. You compute the previous average that you had times the len minus 1 plus the reward that you get right now divided by the current length. And then you also need a method for sample which gets the result from it, and we do a random.sample. So as you can see, there is no priority in here. We're gonna completely randomly select from this, and we're gonna select how many. We're gonna select batch size, and then obviously we're gonna zip it to have them, because right now they are separated in row. We want to have them separated by column, so that's why we do zip in here and we return it. So now I have a batch of different transition of a selection rebar done and lock priority, and then we also have a method for that. But that was the area one, which is basically doesn't have any priority. You can define the priority based on, for example, the reward that you get. So that's what we have in here. So same as before, whatever we had before, for this one I already have as well, but in addition I have a buffer priority and position priority. So this is for my high reward region, and then I have a buffer done and position done. These are when the transition is done. So the transition is actually done in the case of squid hunt when it actually hit a wall. So that's actually equal to when you get a very negative reward. So this kind of supervised knowledge can actually help our replay buffer to be more informative. And then we have the average reward in here as well. So the add is exactly the same as before, nothing changed. And I have the add priority. So add priority, now I will call add priority only if the reward that I get from the specific transition is higher than the average reward. So if it is greater than the average reward, if I get something better than average reward, that's when I add it. Otherwise I won't add it to the add. If the transition that I get is doing better than the average that I already have, I will add it. Otherwise I won't. And then the whole process to do it is exactly the same. And then as you can see, I'm not computing any average in here. The average is only calculated for this priority list. And then we have add done, same thing in here, but the only thing is that I don't have a the average again in here. I'm just going to add it when the done is true. So then if I see the done, then I'm going to basically add it in here as an informative information. So this buffer right now has a capacity 3 times larger than the previous one, because they have add priority and done. Each of them has the same capacity. But then the only difference is that when we are doing it a sample. So the sample, what will happen is that instead of sampling all of it from the buffer, which was the original one, I'm going to 1 minus the ratio. So whatever ratio I have defined by default is 0.2. So 80% of them are going to be done selected from the batch. Otherwise I need to make sure that the done buffer is completed. So if that's the case, then I can randomly select from the if it not the case, if I don't have enough data, I will get the whole from the buffer priority. We are sure that the buffer priority is actually full if the buffer is full, because in the beginning everything that goes inside the buffer also goes inside the priority buffer. And then if I have enough done, then I'm going to select 10% of it, the ratio divided by 2, 10% of it from the done, 10% from priority, and then we're gonna extend our batch, and then we are getting it. So we are sure that each time our batch includes 10% of the priority and 10% of the done state. Then we have our Actor-Critic network. So for the network, what do I have? I try to consider a shared network for both of the Actor-Critic. There is no specific reason for that. You don't have to do it. But then I consider dropouts. So the dropouts that I add in here is because I don't want it to easily get get trained. So I want to add some sort of uncertainty to it so it doesn't overfit. And then I have then actor. So actor convert these 128 to the output dimension, and then I put a softmax. So the softmax results in having all of my output to be a probability distribution. So right now, if I have around 10 output, the output of this actor is going to be the probability distribution of each of those actions. And then for the critic, it's just going to be 1 because I want to evaluate the value of Q in that given S and A. And then obviously in the PyTorch we have the forward pass, which basically do the shared for X, and then we have the shared output and give the shared output for both of the actor and critic, and we obtain the policy and value. But what's important is to get the log probability. So this log probability, why is it important? Because in addition for my transition, in addition to know them what was their value, I also want to know what was the probability of that value that was selected, because we are doing something random. Our policy is basically a stochastic policy, so we randomly with multinomial we're gonna select. So I want to know what was the probability that action was selected, so I want to store it as well. So what we will do, we go the forward step of the state. I get the action probability from the first one, and then the action probability I will compute the log of it, and then when I compute the log I can do the dot gather and then action dot squeeze. So what does the dot gather does is that it will look at this action log probability and try to see that the specific action, what was the log for it. So because the action log probability includes the probability, the log probability of all of the different actions, but among them only one action was selected. So it will tell me that what was the corresponding log probability of that specific action. We have importance sampling. So why is importance sampling is important? Because I'm using an experience replay. An experience replay convey information from some trajectory that was not selected with the current policy. This is an on-policy method. An on-policy method try to update the basic policy based on the latest action that it gets. But when we are using the replay buffer in order to be more data effective, I'm using some of the policy that are different. So if that's the case, if the policy is different, then I need to make sure that I take into the account the difference between the policy back then and the policy that I have now. So how you do it? As simple as importance sampling. So you just divide the probability of them, or you subtract the log probability. I get the policy net, I get the log probability of this state and action, so it gives me the new log probability, and the old log probability was already, this is the log probability from the data, this one was already saved in my replay buffer, so I can compute the ratio, and then I can create a trust region, same as how we have it in TRPO policy optimization. So trust region will make sure that our ratio or how much we are changing from the previous value is not too high, so we are not radically changing our policies. So these are like some conservative methods to make sure that we are not getting divergence too fast. That's when you see, if you look at your result, you're going to see a lot of chattering in your output. So if this trust region was not there, we just easily diverge. But since we are putting a clamp in here and make sure that our ratio remains within the constant, so for example if the constant is 1, the ratio can change from 0 all the way to 2, and that's how we are going to get our trust region multiplied. The very important part is the hyperparameter. So the hyperparameter parameter, what are they? We have actor learning rate, we have critic learning rate, we have a gamma or farsightedness, how much far in the future we're gonna expect, the buffer size or the capacity, the batch size, how many we're gonna select each time, the trust region constraint, the thing that we just talked about, the entropy coefficient, which means what is the coefficient or how much do you want your policy to explore versus exploitation. You have a maximum grad norm, which means that when you are updating your policy or your critic, what is the maximum grad value that you want to get. So this is also important when you are updating. You don't want to have a very high grad values, and that can happen if you have your reward very large, or if you have see some experience that is very different from the current value. And number of updates is basically how many times you want to run it for. For the gym, you can do gym make a squid hunt, or you can do it as simple as carpo. So the carpo is not going to require this much of complexity because of the simplicity of the environment, but the squid hunt actually will give you some knowledge on a little bit more complex, which definitely requires some reward shaping. We'll get into that. And also, in order to install, it doesn't come automatically with the gym. You need to install some packages. I will put the link in the description so you can go and install it for yourself. So in here, obvious, I'm gonna define my buffer, initialize my buffer, my network, create an instance for it, actor and critic optimizer. I will try to pass the parameters of them and then the learning rate of each of them. Then I have a reward list, the frequency of the printing, and then count priority. So I have my training network in here. In the beginning, I have to reset the environment. Then I have some value in here. These are just for saving. So I have commutative reward, commutative actor loss, commutative critic loss, and some counter. As long as we have not reached done, we will keep looping. We create a tensor for the state. We pass it to the network. We get a policy and value. As you can see in here, it's getting some state as the start value. If we don't know what is it and we are in the beginning, it comes from the environment.state, but otherwise we will put the previous value of a state inside in here. So as the policy in here is a stochastic, we have the multinomial, which means that based on this distribution, we're going to select only one action, and when we select this action, we get the corresponding log probability. What is the log probability of it? So I save it in here so that later on I can compute the ratio, and then I do the environment.step. So environment.step, it's exactly same as the environment that we have. It have the next step, reward done truncate. So here is very important part, very easy part to implement, but very important. So if you don't have it, it's not going to work. It's going to be very hard. That is basically our reward shaping. So the reward that we get, if you look at it, is 0.01, and then 5 if you shoot, and then -5. So these changes is like 500 difference between them. We don't want that. So that's why we try to make it a little bit in range, like 1, or you can even make it 0.1, so like 10 times get better if we get a high reward region. So this reward shaping will actually help us not to diverge when we get a good transition. We will add anything to buffer regardless of what is the result is. If the reward is greater than the average reward, I'm going to add it to priority, and if it was done, I will add it to the buffer done. So then what will happen is that if I have enough buffer, then I will do the training. So if we have enough data, which is at least equal to the batch size, we are going to do our training. And this is why we said not to have your batch size too large. So increasing your batch size will increase your variety, but at the same time, you have to wait too long before you update your network, which is not very good. So in here, I will do sample from my buffer equal to batch size. I get all of the information that I require. I obviously convert all of them to torch, and then basically I consider the previous log probability as well, and then I pass it to the network, and then also the next state. So in here I have my state answer, which is current value, and the next state is something that happens after it. I will also need to give it to this to compute the value. Why the value of the next state is important? Because when I'm computing the Bellman equation, the target Q is computed based on current value plus gamma times value next 1 minus 1. So if it is done, we actually don't have the value next anymore. And obviously the reward, if I have the value of gamma too large, I'm going to rely a lot on the value on the previous value, which means that our value need to be more accurate, and it's going to be more far-sighted. However, if it is smaller, like 0.8, then the reward is going to play more role. And obviously I need to compute the ratio, so I use the function I created before based on the old log and then the current value of action. I compute the ratio and then compute the adjusted Q value. So the Q value that we are obtaining here should be adjusted if the ratio that we get is too large or it is outside the trust region. Because the critic loss is going to be based on the MSC loss, the difference between value and the adjusted Q. So very important thing in here is the detach. We need to put the detach because we don't want, when we are training, we don't want it to update the adjusted Q. So adjusted Q is our target, and the target we only want to update it ourselves based on the Bellman equation. I don't want our back propagation to also come and update the adjusted Q. And then the log probability I can easily compute it as the policy new gather, the action based on the policy new, what was the action. So this is the current log probability. This is the probability of that specific action, and then this log probability is going to be used in both of the actor and entropy loss. So what is important is that for actor and entropy, we want to maximize. We want to maximize the basically the actor reward, which is going to be stored in is log probability times Q, and also we want to maximize the entropy. However, since we have the whole thing sorted out in a minimization, we put a negative. So if we put a negative, minimization of a negative value is equal to maximization of the value inside. As you can see, still I have the detaching here because I don't want the actor loss to also have effect on this. And then entropy, again, log probability times the policy new. So I want these the multiplication of this value to be a larger value overall. And then the total loss is actor loss is going to be the actor loss times the entropy coefficient times the entropy loss. The entropy coefficient is the hyperparameter that we have. If we have a higher value, we want to intensive more the actor to explore. And then I have a total loss with this combination actor loss and the total loss. So you can actually do the zero grad for the actor and critic, and then you can do basically critic loss backward, but you need to retrain the graph, because if you do backward, the value are actually gone to save the memory, and then do the actor loss without the return graph, or actually you just do it once with the total loss, which basically compute both of them at the same time. And obviously we want to log it to the Wandb. So after we update it and do the backward, I will do the steps, and then I count the I add the count of the actor loss and critic loss, and also my counter, so I can compute my average. And then I have the reward in here. if I have the counter, which means that if it was more than 1, then I can calculate my average actor loss, average critic loss, and so on. And also I put something in here for a viewing. So now let's take a look at the Wandb result. Here you can see the Wandb result. Here is the ratio. As you can see, we want the ratio to be around some number. We don't want it to be too large. If you remember, we have the trust region to avoid the ratio to be too large, and then here is the reward. These are the value that we said it will stock. So as you can see, it goes around some value and it doesn't go up, so it oscillates. So we talk about how we can approach that. We also have some of the results which actually like this. So as you can see, these are not good because it goes too much high. The actor loss or the critic loss, they go too much high, kind of like diverge and then come back. So the obvious reason is basically having your learning rate too large in here. If you look at this one, that's when we get too confident. In this point, the log probability is actually get 0, which means that the probability is actually equal to 1. So if you look at that, we also see that the ratio after that become equal to 1, the entropy loss becomes 0, and everything kind of like collapse. Even though that an Actor-Critic loss also 0, even though that the reward is not actually good. So if you come back and look at the reward, we see that nothing special change in this point, and then we are just going up and down. There you have it, guys. We went over the code and also the results of how to design Actor-Critic with prioritized replay buffer for a system with a sparse reward. We went over the code, the different components. I've also put the link of the code in the description of the video. Let me know in the comments what do you think, and if it doesn't work for you. If you haven't watched the previous video, make sure to watch it in here, as I went over the conceptual meaning of the sparse reward and how we can design an agent to update it, and I'll talk about the common challenges and what we can do to avoid it. So it's gonna help you a lot in terms of understanding the concept. If you enjoy the video, make sure to like it and subscribe to the channel so you get more information. And thank you for watching until the end of the video, and see you until the next one.